My name is Tejas Kulkarni, and I'm in fifth grade, and I go to Louisa May Alcott. I'm doing this physics course with my dad. I'm hoping to learn a few new things about physics. So we did an experiment, and so we set F net. We pretended that gravity was F net, and there were no other forces acting on our crumpled piece of paper that we dropped from about 10 feet. F net here is equal to minus m multiplied by g multiplied by j hat. J hat is the unit vector, and m is mass. G is the gravitational acceleration. Gravity. This is like the gravity and drag. So we're adding drag. So F net would be the gravity plus drag force on the crumpled piece of paper. So the F net would be W for the weight force and FD for drag force. We know W equals negative m multiplied by g multiplied by j hat, and FD equals a constant, which we're going to call b, multiplied by velocity squared. B is a constant. Notice that we're not using a negative sign for b since the velocity is squared in our models. After some trials, I set b as 0.00047 so that the drag force matches my observed end positions. G is equal to 9.8 meters per second squared. M, the mass, is equal to 0.00293 kilograms. I threw the crumpled paper from about 10 feet high. I think that if the height were more, the drag force would have eventually equaled the weight force according to the model. At that point, the object would reach terminal velocity. Well, we took a video of a crumpled piece of paper falling from about 10 feet. Here is the video. So this is the graph that we acquired from Tracker. Now we are going to show you the same thing on VIDLE. So we're assuming that for this one we're assuming that there is no there's no drag force, and there's like only gravity applying on the ball. So W is equal to minus the ball's mass multiplied by G, which is 9.8, and J hat the unit vector, and F net is W. We're gonna run the module now. The ball speeds up, so we know that there's another force acting on it. So we think that force is drag force. So now we're gonna show you when F net is equal to drag force plus the gravity acceleration. So the W is equal to minus the ball's mass multiplied by G, which is 9.8, multiplied by J hat, the unit vector. FD, which is the drag force, is equal to a constant, which we're calling B, multiplied by the ball's velocity squared. So the F net is equal to W plus FD, and so we made arrows. Well, the arrow scale is 70, and we made arrows to show gravity and the drag force. We're gonna run the module now. Yeah, I think there was a problem. I think it's fixed now. So we're gonna run the module again, see if it works this time. Yep. So the yellow arrow is the gravity, and the blue arrow shows the drag force. So as the blue arrow keeps increasing, and once it reaches the yellow as much as the yellow arrow, that then the velocity will become constant. So now we're gonna show you a graph on about like our prediction and the real thing. So this is a gravity only model. So the blue line is our prediction, and the red line is gravity. So because it differs so much from because the red dots differ so much from our module, our prediction, we're going to that means there's another force acting on it. So this is the gravity plus drag force model, and it's closer to our prediction, but the where it's not so close might be the camera or the x-axis. Thank you.